Yeah, so what we did last time is we started with some function g on m bits, which is hard to write as a sum of squares of low degree polynomials. So g is on m bits. This is the sum of squares degree of g, and intuitively we assume this is large. So d here is the sum of squares degree. D is large. What we said is that, okay, so since d is the sum of squares degree minus 1, sorry, it means that g is not in the cone of degree d sums of squares, which means that we can separate it from that cone by a linear functional. And here were the properties the linear functional had. I mean, this is every linear functional that separates you from this cone has these properties. So just sort of like, this is just a rescaling. So when you take the inner product with the constant function, you get 1. That's just a normalization. When you take the inner product with g, you get something negative. And when you take the inner product with anything in this cone, you get something non-negative. And of course, we only need to ensure that holds for the extremers of the cone, which are just the squares of low degree polynomials. So phi is separating g from this cone. And okay. So then, given this g, now we do this sort of relativization or amplification, where we define the matrix to be. So now we think about things that are in 0 1 to the n. N is larger than or equal to n. And this matrix contains the evaluations of g at all of the restrictions of x to subset of size m. So for every subset of size m, we can evaluate g on the restriction. This gives us a big matrix. It's n choose m by 2 to the n. And then we assume that we have a PSD factorization of this matrix with PSD rank r. Okay, so that looks like this. You write the matrix at S and X as the trace of AS and B of X, where those are R by R positive semidefinite matrices. Okay, and then the last thing we said before is that given such a factorization, there is a degree of freedom. For instance, you can, if you multiply A on the left and right, and multiply B on the left and right by some appropriate matrix, then the effect of that altogether will cancel out. So you can conjugate A and conjugate B. Here, there's a degree of freedom. I mean, I guess the intuitive way to think about it is that we would like this factorization to be well conditioned. So if it's the case, for instance, that some eigenspaces of A have very small weight, like A doesn't put any weight on them, but B puts huge weight on them, then the contribution here would still be small, say, because we have something huge times something tiny. Let's say very tiny, we get something tiny. So sort of that part of the space wouldn't matter, but if you just looked at either component individually, like if you just looked at B, it would look like it matters because it's some huge component of B. So we just want to basically condition the eigenspaces of A and B so that they act nicely together. So, and this was the truncation lemma last time. And the main way you do that is just with a clever application of John's theorem. So John's theorem says if you have essentially symmetric convex body, then you can apply a linear transformation to the space such that the body is contains a Euclidean ball and is contained in a Euclidean ball of radius square root of dimension. So it's sort of a nice way of rotating the space, rescaling the space so that the convex body is not too ugly with respect to the Euclidean measure. So you do a variant of that here, and that's how you get this. That's how you get some sort of smooth factorization. Okay. So the important things here are just and I should say what are these norms. So that's right here. Matrix norms. But those norms, the only ones that are appearing are just the operator norm. So this is the largest eigenvalue of AS is at most R cubed for every S. The largest eigenvalue of BX is at most R to the fourth. What does this mean? This is R to the fourth. So in R dimensions, this is just R to the fourth divided by R. But the point is, after the truncation lemma, I want to forget the dimension. The dimension is not going to matter anymore. So sort of, this is the kind of quantitative thing that we need. as you'll see in a second. Okay. That's the reason I wrote it like this instead of writing it instead of just writing R cubed here. And the matrix norms that we're going to deal with are the operator norm, which is just the maximum eigenvalue, the trace norm, which is the sum of the absolute values of the eigenvalues, and the Frobenius norm, which is the L2 norm of the eigenvalues, and also, let's just write it, L2 norm. Those are the matrix norms that we're going to see. And by the way, in communication complexity, this rescaling really just corresponds to the usual sort of trick, which is if you have two parties communicating, but they don't communicate very much, then they partition the communication matrix into rectangles, right? And if they don't communicate very much, then most of those rectangles have to be large. Most of the input matrix has to be covered by large rectangles. And then basically what happens, you throw away the small rectangles and just work on the large rectangles. This is basically the analog in this section. That we sort of, and by the way, there's something you don't see here because there's a bit of a lie. When we got these conditions, we lost a little bit. We only got an approximate factorization. So what I've done here is I just set the approximation parameter. So we got an approximation to this matrix in L infinity norm, and I've just set the approximation parameter equal to 1 over r, which 1 over r is a very small number from the point of view of the proof. So like this was r squared over delta, and this was r cubed over delta before. So I just set that, and we're just going to ignore that approximation error because it's not the main source. That approximation error is not the main problem. There will be another error which is sort of the main issue that comes up. So you can just trust me, and in fact you'll be able to see from the proof that actually, as long as the L infinity error is less than the L infinity norm of this functional, so then the inverse L infinity norm, as long as the error times the L infinity norm of this functional is, say, less than 0.001, everything will be fine. So there's going to be another source of error. Let's just ignore this error. It's not the main, that one is easily controlled. So now we'll just assume that our factorization looks like this.
It's a silly thing. ID is the
identity, and it's just the identity in whatever dimension we're working in. So
the bottom line should be a number.
Yes, good. So this should just be 1. Good. Thank you. Proof should at least type check.
Why do you call it truncation?
Because what we did to get here was, we rescaled, and then basically we deleted all of the small eigenspaces of, we deleted all the small eigenspaces of A. They weren't contributing to the expression, and but they would make it so that if you look at sort of the whole space, kind of the factorization could sort of be hiding in a tiny. All the interesting things could be going in a tiny portion of the space. Which is not going to work well for now what we were doing last time. So what we said last time is two things. So number one is that if we so now basically what we're going to do is so remember phi s here is again. Phi separates G from this low degree cone on M things. Sorry, this is supposed to be M. And I guess we should put here that this Phi S is on things of length N. So it's just the applied to input X. It's just looking at this M-dimensional space on the subset S. Okay, so so now the hope was last time that if we apply this functional to one side, we'll get something negative. If we apply it to the other side, trace AS BX, we'll get something positive, and that will show that the factorization could not exist. So basically, assuming that the rank R is small, the idea is that this functional is supposed to separate the two sides, showing that in fact R could not be small. So last time we showed that this is in fact equal to the inner product between phi and g, which is less than 0. And if you remember, it's just because this is the restriction, this is g restricted to s, so if you just, this is phi restricted to s. So if you just look at what happens here, you're just seeing many copies of the inner product between phi and g averaged over every s. You're just seeing the same number averaged many times. And the other thing we said is that if b is a low degree square, so if the square root of bx, this is the matrix square root of this matrix, it's a positive semi-definite matrix, take the positive square root. If the degree of this is less than d, then we indeed get a separation. Trace AS BX is non-negative. And this is a matrix, so to remind you what the degree of a matrix is. So the degree of just some matrix valued function is just the maximum over all of the indices of the degree of just the maximum of the degree of its entries as real valued functions. So the point is, if when you take the square root of b, and by the way, you get a matrix where every entry is a degree d function of x, then indeed you separate this. Okay? And I don't want to write it down the calculation again, because we need to make some progress. But the point was that, I'll write down the expression. This thing, what is also, it's the same as this Frobenius norm squared, and if the square root of b is a low degree polynomial, then this is a sum of squares of low degree polynomials, and then when this phi acts on the square of a polynomial degree at most d, it always spits out non-negative things. So we get non-negative over and over. And now our goal today is to just take our b that we have coming from the truncation lemma and approximate it by a low degree square, so that this separation argument works not just under this assumption, but the separation argument should work for the approximator, and as long as the approximation is good enough, it will also provide a separation for d itself. By the way, if you're like, this is a confusing. If you take the matrix square root and you look at the entries and you ask for it to be a low degree polynomial, I won't be affected. Like doesn't make that's sort of like that's not something which is intuitive, like what that means. So we want to approximate b of x by low degree square. Okay. So now let's write down the. Okay, and the key, by the way, here is that you're not going to be. Look, b is fairly arbitrary. We're going to say that it can't be too crazy, but you're not going to hope to approximate it point-wise by a low degree square. The key here is what's the correct notion of approximation, so that the proof we want to do still goes through. Okay. So now let's just have so recall. So let's let d plus. I'm just using this notation, so it's similar to s plus. This is a set of matrices Q, positive semi-definite matrices Q, with trace 1. So those are the density matrices. Just a set of things with trace 1. Those are the ones we can think about as quantum probability distributions. Notice that if we insist that the trace is 1, if Q is diagonal, then this is just k positive numbers that sum to 1. It is indeed a classical probability distribution. And here's the sort of the approximation problem that we want to solve. So we're given some density Q, and tests. Okay, F1. Let's just call them. We don't have to number them. So call them tests, Fi. The tests are just symmetric matrices. Okay, so we have a bunch of tests. And we're given some error parameter epsilon. So we have Q, we have some error that we allow ourselves, and then we have these tests. And the idea is that we would like to construct an approximator that does almost as well on the tests as Q does. Okay, so what's the notion? So we would like to find a simple density Q tilde. Okay. So hopefully over here, simple is going to mean low degree square. Such that trace Q tilde Fi, this is the value of this thing on the ith test, is at most trace Q Fi plus epsilon. I just want to say this is sort of, and I say it in more generality than we're going to need, and we'll just do it for the generality we need, so the proofs are particularly simple. We're just going to have one test, actually. Okay. In fact, you can sort of see what the test is going to be. The test is going to be the one that makes sure that those two expressions are the same for B and for the approximate version. That's going to be the test. But the strategy is sort of somewhat more general. In fact, the number of tests actually doesn't matter. It doesn't affect the quantitative thing. But sort of, is the problem clear? We just sort of have some notion of we have some tests that are linear functions of the matrices, and we would like to have a Q tilde, which we only require do well on the tests. And since we're obviously Q, we can have Q tilde equals Q, but since we're only requiring them to have similar behavior on this set of tests, which might be very special, it makes sense that maybe we could construct a Q tilde which is nicer than Q. So we're putting fewer requirements on. It doesn't have to be Q, it just has to be something that does as well in the test as Q. Okay, I'm going to say the theorem now. This is how you should think about the statement of the theorem. As sort of constructing a simple approximator that passes the tests. And we're just going to state it for one test. Because the proof is particularly simple. Although I will say that the real power of this is that the quantitative bounds don't depend on the number of tests. So if you had an infinite number of tests, the quantitative bounds would be the same. So here's a lemma. We'll just do it for one test. So given, again, a density Q and a test F, which is just a symmetric matrix, and also our error parameter epsilon. So there exists univariate polynomial P such that, so here's going to be our approximator. Our approximator is going to be P of the test squared divided by, okay, this is just a normalization to make sure that this thing is a density. So it's some polynomial of f squared divided by the trace. And we want that to satisfy that it does as well, almost as well on the test as Q. And so far this would not be so interesting, but the last thing is that the degree of P is small. So the degree of P is at most some constant over epsilon times the operator norm of the test times, and we're going to define this in a second, although James defined it yesterday. So it's at most some, C is a universal constant. I don't know that tensifies, so I'll just put the C back. Okay. C is actually C is can probably be set to like the constant 3 unless there's something uninteresting happens, then this is sort of, okay. I didn't tell you what this is, so let me tell you what this is. But the idea is that given a test and given Q, we can find an approximator that's a low-degree polynomial in the test F. Okay, where low means that does as well in the test as Q did, so this is error epsilon. Where low means the following. Okay, so we have some dependence on the error, that's natural. The better the error, you expect that maybe you need something more complicated. We have a dependence on the operator norm of the test, on the maximum eigenvalue of the test, which absolute value of eigenvalue of the test, which makes sense. If this test was very sort of precise and insisted that on a tiny piece of the space you had some very exact kind of behavior, then it seems that that you might need to do something more complicated. So this is sort of measuring how complicated the test is. And then this is also only going to work if Q itself is not too crazy. So we're going to define this now. This is the relative entropy between Q and the uniform density. I'm using S for not for any great reason. In James' talk today, it was D. So this sort of measures how nice Q is. So if, for instance, if this quantity, so for instance, if Q was just I guess first let's say what U is. So U is, let's try that again. So U is just the identity matrix scaled to be a density. So it's called the maximally mixed state in quantum information. So for instance, if Q was equal to the maximally mixed state, then the relative entropy here would be 0. And that would make a lot of sense because we could just take P to be the identically 0 polynomial, and we would get a very good approximation. Like if this Q was this U, then this would be 0. Okay, and of course then our approximator could just be have the polynomial P be 0, which would mean that what does it mean if that would make this 0? I guess at 0 there's a bit of a problem. You sort of have to take a limit because of this scaling by the trace. No, so I don't know what I'm talking about. We take P with the identically 1 function, and then we would get the identity matrix. Okay, and then the degree effect of the constant is 0. Yeah. So if we just took P to be the identically 1 polynomial, this is a matrix value polynomial, so 1 means the identity matrix. Okay, so then the point is we would get a degree 0 approximator. And the idea is that now as Q becomes more complicated in the sense that its relative entropy to the uniform density becomes larger, we need a more complicated approximator. Where in general between two states Q and P, this is Q log Q minus log. This is the quantum relative entropy. So is the statement clear? So basically what I want to do now is show how the statement gives the goal and then prove the statement. That's the plan. Okay. So let's now apply the state. Let's assume for a second that the lemma is true and apply it to B. Except I want to package B up into a single matrix. So let's define now. Let's define now Q to be the notation here is not so interesting, but basically Q is a block diagonal matrix which just contains the B's on the diagonal. Okay, so I just take this B, which is a function from 0, 1 to the n to matrices, and then I just make a giant block diagonal matrix where this is maybe B of all zeros vector, and then here is B of all ones vector, and then you have all the things in between. And it's 0 in the off diagonal. This is a giant block diagonal matrix. I'm just taking my B, and instead of encoding it as a function, I'm encoding it as a matrix. And this here, this is just some orthonormal set of vectors in some new Hilbert space. So this is a 2 to the n orthonormal vectors, just so that this definition makes sense.
Yeah. So the trace of q times log q is understood to be 0 if q is 0.
Yeah, if q is 0, then in general, not just that, but if so this expression without the p. This thing is complicated when q and p are not simultaneously diagonalizable, because then it doesn't make any sense at first glance.
Yeah.
But for just q, this expression is just this, and then indeed 0 log 0 is interpreted as 0. Okay, so this is our q. So we're going to apply this theorem. So the first thing we'd like to do is bound the relative entropy of this q. Okay, so let's do two things. First of all, I guess first we need to make sure that q is a density matrix. So to that end, let's assume that this, which if you think about it, is just the expected value of gx equals 1. Okay. So I didn't do any scaling so far with anything. So I'm allowed to scale things one time, right? So this is my one scaling. So I just scale g so it has an average value 1. This is going to make the computation simpler. Does it affect anything? Possibly, because actually the error in the truncation lemma actually depended on the maximum value of this matrix. But I guess we didn't write the theorem again. Right now we're allowing ourselves to lose a constant depending on g. Like g is fixed, and we can lose a constant depending on g. So the L infinity norm of this matrix is just the maximum value of g, and the L1 norm here is just the L1 norm of g. So, and moreover, all of the ratio, for all of the g's that we would consider here, the ratio between the L1 and L infinity norm is small compared to everything else. So it's not even a moral hazard to do this, but let's assume this. And the point is that under this normalization, q becomes a density because right. So let's say the trace of q is the expected value over x of the trace of bx by construction. Let's do the minus n there. And then this is the same as the expected value over s and x of trace as dx. Because of our assumption 1 that the expectation over s of as is the identity. So I just multiplied inside the trace by the identity here. And we use linearity as well. But like if you pull this, if you push this inside, then and you take expectation over s, this is the identity. So this is just the same thing. And this is this, which is 1 by assumption. Okay? This didn't. We could have just normalized q to be a density and then carried this normalization all around. So this is just for convenience. This rescaling, nothing interesting happened here. But now, so the point is now q is a density matrix. Let's evaluate the relative entropy of q with respect to the uniform density. And to do that, we actually can just evaluate the operator norm of q. So my claim is the operator norm of q is at most r to the 4th divided by the trace of the identity. Okay, why? Well, the maximum eigenvalue of any b is r to the 4th over the trace of the identity in whatever dimension we were here, and here we divide by the new dimension. The new dimension is 2 to the n times the dimension here, so we divide by 2 to the minus n. So indeed we get r to the 4th divided by 2 to the n times the dimension of b, which is indeed the dimension of this q. So the point is that q is bounded like this, and then now we just do the computation here. So what is this? This is just the trace of q log q times the trace of the identity. Okay, because what I mean, we plug in q, so we get q log q, and then we plug in the maximally mixed state here, we get the identity divided by the trace. And so it's sort of like minus log of 1 over the trace is log of the trace, and then log a plus b is log of a times b. So this gives us log of the trace. And now the point is that just bound this by bounded by the trace of q times the operator norm of log q. Let's do this. The log of the operator norm of q times the trace of the identity. Okay, so I just now we just use an easy held here, which is the inner product is bounded by the one norm of q times the infinity norm of this thing, and the infinity norm of this thing is exactly log of the infinity norm of the operator norm of this thing, which is this. And the point now is that this is 1. This is the trace of q. This q is the density, and so we get our goal in this part, which was that the relative entropy of q to the maximally mixed state is only order log r. So this was sort of the whole point of doing this rescaling, that what it says is that, B is very sort of well spread out in this space. Even if we lift B, then it's the largest, okay, when this is 0, it means that we're at the maximally mixed state, okay, which is sort of the simplest, that's sort of the simplest matrix we can think of, and the simplest density we can think of. And but this could be as large as, this could be as large as log the dimension. In fact, the dimension here, we don't even know what it is. It's something huge. But when that's a very tiny value. This means this thing is very, very close to being the uniform measure in the relative entropy distance.
Could you go over how you get the log r?
So it's just log of q times the trace, and now the operator is r to the fourth over the trace. So it's log of r to the fourth. But maybe it would be even better if I just written 4 log r.
And what about the trace norm of q?
That's 1. That's what we verified here.
Oh, okay.
We did this calculation, but in general, if you have a density and the operator norm is bounded, immediately implies that the relative entropy is bounded. Just like if you have a density in the classical, like if you have a density with respect to a classical probability distribution, if the L infinity norm of the density is bounded by R, then the relative entropy of the density is bounded by log R. For the same reason. Okay. So the point is, we want to apply this. So now we've confirmed that our Q is not too complicated. And by the way, this is sort of crucial here. The point is that R is something like really big. Either it's exponential or it's like n to this d. So it's crucial that we're only going to pay something depending on log R here. If we pay something depending on R, then the game is lost before we start. So that's okay. Good. So now we verified that Q is simple. I guess we should also define what's the test that we're going to use. So the test is also it's the natural one. Here we lifted Q to a big matrix. Now we just want to lift also, we lifted B to this big matrix. We also just want to lift A to a big matrix too. Equals the test. Actually, this whole thing here. So the test is sum over x phi s x expectation over s phi s x as. That's going to be our test. And the point of the test is just that, that still doesn't make sense. Soon it will make sense. We're going to put it in this block diagonal form. Okay. And the point is just that all this is doing is, when you take the inner product of f and q, it's just the It's just the sum of the inner products of the blocks, which is going to be exactly this expression. So the point is that trace FQ is exactly, that's exactly what we want. So I feel a little bad because that, so again, we haven't really done anything yet. We just sort of like, we just package everything up into the big matrix and into these functions. But now the point is that the value of our test at Q is sort of exactly the kind of thing we want. So, I mean, it makes sense that if we have an approximator, we would like this is the test that we care about, right? We would like because what's our goal? Our goal is to say, we'll take an approximator, which is low degree. Then when you plug the approximator in, you get something non-negative. But the performance of the approximator and the performance of B are within epsilon. So when you plug in B, you must get something that's at least minus epsilon. That's sort of our goal. So I'm just saying, this test makes sense. It's exactly what we care about. Okay, so the point is now we apply this with this Q and this F. And I just want to check that our by the way, I guess it makes most sense to go like this, right? Because then your movement is continuous. You start again on the left side of the board, and you have to jump. Sorry. I'm apologizing for the fact that I'm now writing right to left, but then I was trying to pretend that that's for the sake of the audience. Because you're never too far from where you're supposed to be. Is there a question? Okay. Yeah, so let's see that this sort of this finishes things. Okay, so now we have, so apply the lemma with some epsilon. So I gave you Q and I gave you F. You need to sort of, we specify epsilon later when we see how much error we can afford. What's the, okay, so we get an approximator Q tilde, which is a polynomial in F squared, normalized to have trace 1, where the polynomial satisfies some degree bound. Okay, and then I don't necessarily know even the correct notation for this thing, but then we define our B tilde just to be like unpack this Q. So it's it's Q tilde in the XX block. I mean, actually, we should actually multiply it by 2 to the n to take off the 2 to the minus n. But the point is, given a block diagonal matrix, I can reverse this operation and go back and get the B's. And why is the approximator block diagonal? Well, it's a polynomial in F, and F is block diagonal. So this approximator is also block diagonal. So we can go, and first of all, it's clearly non-negative because it's a square. So we can go backwards. So I'm just saying, we get this Q tilde, we go back, we get this B tilde. Such that we get sort of the property we want, which is that trace of AS B tilde X, sorry, this thing, so it's equal to trace F Q tilde, which is at most, which is at most, have the approximation guarantee. So it's trace AS BX BSX plus epsilon. So we get this B tilde. When we plug that into this expression, it's at most the original thing. We want to prove this thing. We wanted to prove this is non-negative plus epsilon. So if the degree of B tilde was small enough, then by this observation we would get that this expression is non-negative, and so this expression would be at least minus epsilon. So that's sort of the we exactly tried to construct an approximator for the one test which matters, which is to get the proof to go through. is the approximation guarantee of the lemma. It says that, I guess I was writing things in the other way. Of course, you can commute under the trace, but maybe just for... So, okay, so B tilde does as well in the test. And now what's of course, I guess the last question is, what's the degree? So first of all, it does well in the test. Secondly, it's a square. Okay, so this thing is the square of some matrix, but it's a block diagonal matrix. So every block of this matrix is indeed the square of the matrix P of F restricted to the P of F x x. Okay, so sort of this matrix is again block diagonal, and it's a square of some other matrix. So indeed, all of these things are squares. All the blocks are squares. So the only question left to ask is, what's the degree of the square root of B tilde x? And okay, so what is it? It's at most the degree of P times the degree of phi. Okay, so let's see. P is a function of f. Okay, but the degree is the maximum degree over all of the degrees of the blocks. So let's just consider one block. One block is okay. So we get this. Yeah. Okay. Good. This makes sense. So one block is just. One block corresponds just to looking at this thing. So the point is, every one of these things is P applied to this matrix squared. Again, you should think about this as just saying that this is a matrix with a bunch of blocks indexed by x, and every block is this matrix. And so the point is that the blocks here are squares. What are they squares of? They're squared of some polynomial in this expression. So some P applied to this matrix. So if P has degree, you have it. So the total degree is at most the degree of P times the degree of this thing, and the only dependence on x here is this. So it's just the degree of this phi s, which is the same as the degree of phi. So just every block here has some degree that's the degree of phi, and now we just take a polynomial of that block. So we at most multiply the degrees, and now so now we got what we want. What's the degree of P? C over epsilon times log r. I omitted the 4. I'll absorb it into this constant c and say that this c is different from that c. Just some constant over epsilon times log r times the operator number of the test. So I guess we should do that calculation. It's very simple. So the operator number, again, it's a block diagonal matrix. So the maximum eigenvalue is just the maximum of the blocks. So we just ask ourselves, what's a bound on the eigenvalue of this matrix? And well, remember that if we didn't have this, then this is just the identity. So just a little fact here. That's the most the L infinity norm of phi, phi s, but the L infinity norm is the same, times the operator norm of this thing, which is just the identity. So it's just the L infinity norm of the test phi. That's from property 1 of the truncation norm. Just that this thing averages the identity. So now good. So then we get here times the L infinity norm of phi, and then the last thing is, what's the degree of phi? Okay, let's just use a trivial bound degree of phi, which is that phi is a function of only m things, so its degree is at most n. So that's so we get a bound on the degree of the square root of this approximator. What the important thing to remember here is actually that this is all just a constant depending on g. M is the constant depending, if we're really allowing ourselves to lose constant depending on G, M is the constant depending on G. Actually, don't think about M as M is the constant depending on G. The L infinity norm is the constant depending on G. This is really like log R over epsilon times some constant depending on G. And this is our, okay, this is what we said we wanted last time. This is our medium degree approximator. And what I mean by medium degree is, in order to apply this argument, we wanted the degree to be at most D. We're definitely failing on that now, because our degree is M times some big number. And D has to be less than M, because, I mean, D is the degree of the sum of squares degree of G minus 1. But G is only on, inputs of size M. So each degree is certainly at most, each sum of squares degree is certainly at most M. So like we're way over it. I mean, we got something non-trivial, but it's not nearly good enough to apply. But it's good enough where next time in the final in the final lecture, we'll be able to use this random set S with the random restriction argument to say that for most sets S, when you sort of look at things on S, this degree becomes very small, less than D. Sort of like, so getting from medium degree to low degree is the whole point of the random subset. That's where, or at least that's where the random subset comes into the proof. Now we're just left to do the lemma, which is where the work is going. So I just want to say we can apply the lemma to our setup. Now you couldn't forget everything and you just try to prove the lemma the last 10 minutes.
So I don't want to be ahead.
Yeah.
Sometimes you use a trick where this phi, you can assume that it's degree at most d because it's a function applied on d polynomials.
Yeah.
Couldn't you do this there and get this m down to d? Is it useful?
So for us, if you remember, like with the knapsack polynomial, d and m were proportional, right? For knapsack, d is m over 2, so it's not helping us so much. The answer is yes. You could use instead of m here, you could use d. It's but okay, it doesn't here. It doesn't help, and yeah, it doesn't. It helps actually somewhere else, but here it doesn't seem to help. Although I mean, okay, so it would definitely help if there are cases you might care about. Actually, where d is much smaller than m, and then it would be better to use d. Right? Here we're not even sort of worrying about the distinction between d and m because they're all just constant depending on g, right? And we're allowing ourselves constant depending on g. But you're right. A better bound you could put here is d, and that's just because it makes sense. Yes, you could bound the degree here by d without loss because we only have really a restriction on, phi for degree, that thing's a degree at most 2d. And so, we can delete the part of phi that's orthogonal to the, that's above degree 2d. But, okay, it's not, we don't need to do it here. Okay, so let's just do now the lemma, and then we're done. And the lemma is, it's very, it's a consequence of sort of the duality formula for relative entropy. So let's prove the lemma. Okay. So consider the following map. We map x to trace, let's say, fx plus the relative entropy between x and the maximum state. This is a map of x, and we didn't see it, but this is to a sort of what Jane mentioned yesterday. This is particularly easy. This is a convex function of x, so this whole thing is a convex function. It's a linear function plus a convex function, and you can think about it as sort of like it's. We want to find the minimum value here. So here's an assertion that x hat, which is e to the minus f, divided by trace e to the minus f, is the unique minimizer of this thing over density matrices f, over x, which are density matrices. So I take this map, and I minimize it, and I claim that this is the answer. And then we should think about this map as sort of as being some kind of entropy regularized optimization. I care about my performance on the test. I want to do really well on the test. But I also don't want to be too complicated. So I add a penalty term for the entropy of x being large. So the claim is that the solution to this is this. Okay, so why is that? So we need one. We're just going to use one fact, which is that the relative entropy between two matrices is always non-negative. So for any x, for any density, this is greater equal to 0. Okay, so I was seeing if we have time to write it out. Let's just, basically, when we write out this inequality, it will exactly claim that x hat is the optimizer. Let's start. So like, this is true. This is a slightly non-trivial fact. It actually follows from the fact that this function is convex in x, which requires doing a computation. Okay, so this is the claim. Okay, so like, okay, I mean, this is our claim. We haven't proved this yet. This is true. Okay, so let's analyze it. Okay, so what is it? We have to look at the definition. It's trace x log x minus trace of x log this thing, which is, so what do we get? We get minus fx, and then plus log of the trace of e to the minus f times the trace of x. So I just plug this in here. So the first term in there is x log x, which I didn't get rid of. The other term is x log x hat. So what is x log x hat? We get a minus f times x from here, and then we get log of this thing times, which is just a constant, times x. And the point is, x is a density matrix, so this is actually trace of x is 1. So that's the expression for the relative entropy. And the fact that it's non-negative means what? It means that the trace x log x is, move this over to this side. Okay, actually, good. Is at most, plus this minus, is at least minus log trace e to the minus f. I just subtracted this to the other side and use the fact that minus is plus. Okay. And note that this thing here is this thing here is precisely this, except for there's an additive constant. We're looking at minimizers, so the additive constants don't matter. There's an additive constant coming from the fact that from the trace of the identity. But we've basically said that this is at least minus this. Okay, so now let's just calculate. Let's calculate the same thing for x hat, the same expression. So x hat plus trace f x hat. Okay, so let's see what happens. We're going to get, so we look at this log, we're going to get minus f times x hat, which is going to cancel with this thing. This is trace fx hat. Here we're going to get, from the log of e to the minus f, we get minus fx hat, that cancels. So we're only left with the denominator, and we get minus, we get the same thing as we got before. Okay. So you see that for x, this thing is greater than or equal to the value for x hat. So that implies that x hat was indeed the minimizer. And when I said unique, it's just because this function is actually strongly convex in x. So if x and x were not the same, you would have strictly be within 0. You get that. Okay, so that was the. I will be on time. I mean, if this is confusing, that's, like, why did it work? Was it magical? There's a whole, there are thousands of people in various areas that, study this kind of regularized optimization problem. And it makes a lot of sense as something to do. You can think about it in a different way, which is sort of that you're, sort of subject to some performance on the test. You're trying to maximize the entropy of your density. Maximize, not the relative entropy, but maximize the sort of the von Neumann entropy. So the point is, like, you want to do well on the test, and this thing is encouraging the simplicity that we're searching for in the lab. Okay, so this is the unique minimizer. In particular, this implies that. So now just replace. Here I have it. Here I didn't. What's the trade-off between these two terms? Now I'm going to replace just f by lambda f. So x hat equals e to the minus lambda f over trace e to the minus lambda f minimizes lambda trace f x plus relative entropy. I didn't do anything except replace f by lambda f. Okay. This one makes more sense now. We're saying how much do we care about accuracy on the test and how much do we care about the entropy, and we can change this now. Okay, so and now you see that. So what does it mean? It means that lambda times trace f x hat plus this. This is the minimizer. So sort of if we plug in q, we definitely get something which is not. Oh, that's good. This thing is non-negative, so just ignore it. It says this thing is less than or equal to this thing, and what it implies is that trace of fx hat is at most trace of fq. Notice this is what we want. Our approximator x hat is performing as well as fq, but here we get this divided by by lambda. And now we choose lambda to get epsilon. So now choose lambda equals the relative entropy over epsilon. Okay. And what we conclude is that x hat, which is e to the minus, let's say it's sort of like, let's choose this as our lambda hat. It's like our good value for lambda. E to the minus f over the trace of that thing. It's written here, but I just say it in words. This matrix does well on the test. We just wrote it. Like we said this to be this is at most epsilon. So we have this x hat, which is doing well on the test. X hat is not a low degree polynomial in f yet, but it is at least a function of f. Right? We wanted our approximator to be a low degree polynomial. At the moment, our approximator we constructed is e to the minus some constant. Constant is this times f. Renormalized. And when I said it's epsilon good, I just mean this inequality. We're getting epsilon good performance on the test. So what's the last thing to do? It's trivial. Approximate e to the x by its Taylor expansion up to some point, and then we get a polynomial. Okay. We need the square of a polynomial, but that's not. That's sort of,
So do you want to allow a bit of room?
yes, okay. So, what Albert is worried about is that we already paid epsilon, now we're going to pay more. Okay, so we put 2 epsilon. And we get, now we're doing epsilon over 2 on the test, and we can pay another epsilon over 2 when we approximate this by by logarithmic polynomial. Okay, so if we just let this be the truncation of the Taylor expansion of e to the x, then Taylor's theorem using the following fact. If you look over all x's, say, between minus b and b, e to the x minus this is at most, let's say this is at most delta times e to the x for m. Okay, so basically I want to get a something which is a multiplicative delta approximation. I want my error to be delta times e to the x. I have a bound b on the value of x. The question is how large we choose the degree. And you can see that we should choose the degree to be, so the following suffices. So let's say 3b plus log delta over log delta. Delta is going to be a constant, so this doesn't matter. This is tiny. But in general, I mean, like look at the m plus first term here. What is it? It's like x to the k over k to the k. So when how do we get that to be small? Well, choose m to be like the maximum value of x, and then at that point we get plus. I mean, okay, I gave you some slack, but basically, if you want this to hold, you should. Okay, is this clear? This is what you should do. The remainder is like this log delta over log delta. I mean, this is not very interesting, but the point is the remainder term here is at most b to the m over m factorial. Maybe use b to the m plus 1 over m plus 1 factorial. So if you want that to be small, you should choose m to be about b. Then because this is growing, this is like this is like m to the m, and this is like b to the m. So you should choose m to be constant times b, and then this will be small. Does it make sense? That's what I'm saying. This is at most. I'm just say something trivial like b over m plus 1 to the m plus 1. So if you want that to be 1, you should choose m to be. I mean, this is a gross overestimate, but choose m to be about b. And then if you go a little further, you get also even smaller than 1. But I think that's not. Okay, so the point is this tells us the degree of our p of p sub m, and what we're left is just to figure out what is this b. So here's a b.
On the right hand side there,
Yeah.
it should be e to the b or something, or delta times e to the x.
No, this is correct. If x is smaller than b, you'll get something better. If it, like here I did the worst case where it's b. But if x is smaller than b, then I get a better approximation.
What is x?
X is anything. So I see. Yeah, I see.
Oh,
The
okay.
soup. So that doesn't make any sense. No, you're right. It doesn't make any sense. So suppose we want this approximation to hold uniform, and I see. For all we want this to hold. If we choose m to be this large, then it definitely holds. And the question is now, what is our bound b here? Well, it's just lambda bar times the maximum eigenvalue of f. You need to see that when you apply the matrix exponential, of course, you're applying it to all of that. This approximation is going on in every entry of the matrix. But b here is lambda bar times f, which is at most this over epsilon times this. Okay? So you see that, I mean, the degree of this p sub m that we need it's exactly sort of it's exactly what we wrote here. Maybe times 3, and then but this is the bound rated on p sub m. And then the only thing you would say is, look, you've constructed an approximator for e to the x, but you should have approximated. So that but you want it to be we want our eventual state to be the square of a logarithmic polynomial. And right now you just like so now what's our naive thing? And then we're done. Our naive thing is this is define this as p m lambda bar f over trace this thing. Okay. So what we just argued is that if we choose m large enough, then the L infinity error of this approximator to our x hat is small. But this is not the square of a polynomial. So instead we just divide by 2 and then square. Divide by 2 and then square. And this is just using the fact that you write e to the minus lambda bar f. That's the way you like to approximate it. Write it as e to the minus lambda bar f over 2 squared. And then apply the approximator to, now approximate this by a Hilbert polynomial, and then you square that thing. Okay. So that was the whole, that's the whole proof. It's really just, you write down this optimization. You can actually, here I did the proof, but in general you could just calculate what the optimal solution will look like. Okay? Just by, setting the gradient equal to 0 and checking, you have to, there's a bit of a, this is a constrained optimization problem because we're optimizing over the density matrix, so you need to add a Lagrange multiplier for that constraint. Then it becomes unconstrained, set the gradient equal to 0, and you just see that the optimizer is of this form. So that's all we did. This optimization problem was the key. The solution to it is exponential in the test. And now, if we have a bound on the maximum eigenvalue of the test, we can approximate this by a low-degree polynomial. So that finishes. So that gives us an approximator by a polynomial of degree. I'll just remind you so that we can use it for next time. 1 over epsilon times the L infinity norm of phi times log r times m. And sadly for me, I ran out of letters. This m is not the same as this m. This m is this m. This m was a free parameter that we chose. But now we're done with constructing this medium degree approximator. And by the way, the same thing holds if instead of having one test f, you could have an infinite family of tests. Everything would hold exactly the same. You have to replace this by the maximum over all the tests. And now instead of a polynomial in one test, you'll get a low-degree polynomial in all the tests. But still, it's, the same thing will hold. Okay. Questions? Yeah. I will say that this part is a little bit magical. The form of this approximator is sort of like exactly what you would expect. The fact that you then can approximate it by something low degree, I don't know. It's nice that it works.